Remember the hare and tortoise story your granny read to you in your childhood? The story goes like this. A hare was watching the slow progress of a tortoise on a path in the jungle. Being a faster runner himself, he began to make fun of the tortoise. The tortoise challenged the hare to a race, and the hare accepted confidently. When the race began, the hare shot ahead and ran briskly for some time. Then, seeing that he was far ahead of the tortoise, he decided to sit and relax for a while before continuing the race. He soon fell asleep. The tortoise, plodding on, overtook him and finally won the race. The table provided shows the data on their progress during the race. Similarly, the graph represents the same data. Can you see how the hare was making progress? But the hare lagged behind in the end because he stopped at 1.8 kilometers. The tortoise, on the other hand, walked without stopping and made steady progress. Isn't it easy to make out who won the race and how? Graphs help us communicate information visually. They enable us to understand quickly trends that would otherwise need lengthy written descriptions. As you have studied in mathematics, a straight line graph helps in solving a linear equation with two variables. In this lesson, you will learn about graphical representation of motion. At the end of this lesson, you will be able to explain how graphs can be used to represent and solve problems related to motion, plot various types of distance-time graphs, calculate the speed of an object at a given instant using the distance-time graph, plot various types of velocity-time graphs, calculate displacement using a velocity-time graph, identify the significance of equations of motion, derive the equations of motion, and explain the concept of uniform circular motion. Graphs typically contain both an independent and a dependent variable. For example, consider the graph shown. It plots the runs scored by a cricket team in a one-day match. If you observe the cricket match graph, the number of overs bowled in a match is independent of how many runs came off an over or how many wickets were taken. Since the number of overs is an independent quantity, it is taken on x-axis. Similarly, we can use line graphs to describe the motion of an object. In motion graphs too, physical quantities such as distance or velocity show dependence on time, while time is an independent quantity. Therefore, time is always taken on the x-axis and the other physical quantities are taken along the y-axis. You can create graphs in motion by comparing distance, displacement, or velocity to time. By representing the motion of an object graphically, you can infer the nature of motion, determine its position at any interval, calculate its acceleration, displacement, velocity, etc. at any instant, and derive equations of motion. Two of the most commonly used motion graphs are the distance-time graph and the velocity-time graph. A distance-time graph represents the change in the position of an object with time. In such a graph, time is taken along the x-axis and distance is taken along the y-axis. The graph is plotted adopting a convenient scale for the distance and time. For example, you can use a scale of 1:10 on the x-axis for time. A scale of 1:10 means that each unit on the graph represents 10 seconds. Let's see how a distance-time graph is plotted using some sample data. To plot the distance-time graph, we begin with fixing two axes, X and Y, on a sheet of graph paper. On the X-axis, we mark the equal time intervals according to a convenient scale. Say 1 unit equals 10 seconds. Again, using a convenient scale on the Y-axis, we mark the Y-axis at equal intervals. For example, as mentioned earlier, your scale could be 1 unit equals 10 meters. For each set of figures, locate and plot a point at which the perpendiculars drawn from the respective time and distance values on the axis intersect. Finally, we connect all the points, starting from the origin using straight lines. This gives us a distance time graph for the data provided. Considering the nature of the motion of a body, a distance time graph may show a body at rest, a body with uniform motion, and a body with non-uniform motion. If a body is at rest and does not move, we say the distance travelled by the body is 0, no matter how much time has elapsed. The distance time graph for such a body at rest is plotted as a straight line along the X-axis. However, consider a situation where the body has already travelled a distance of 5 meters. When we start analyzing data on its movement, it means that the body is at 5 meters at 0 seconds. If the body continues to be at the same position for the rest of the time, then the graph is a straight line parallel to the X-axis. When a body exhibits uniform motion, it travels equal distances in equal intervals of time. For example, consider a body moving with uniform speed. The data provided represents the position of the body at different instances of time. The initial position of the body is 0. The graph for this body is a straight line, making an angle with the X-axis and passing through the origin. Thus, the graph of a body in uniform motion is an inclined straight line passing through the origin. When a body exhibits non-uniform motion, it travels either unequal distances in equal intervals of time or equal distances in unequal intervals of time. For example, the table gives the position of a body at different instances of time. When we plot the distance time graph for the data given, we observe that the distance time graph for a body having non-uniform motion is a curve. Let's analyze this data further. During the first 10 seconds, the distance travelled by the body is 5 meters. Thus, the speed of the body for the first 10 seconds is 0.5 meter per second. For the next 10 seconds, the distance covered by the body is 10 meters. Hence, the speed of the body during the second 10-second interval is 1 meter per second. We observe that the speed of the body increased with time at a constant rate. Hence, we can say that the body moves with uniform acceleration. Thus, for a body with uniformly accelerated motion, the distance time graph is in shape of a parabola. Now let us consider a body moving unequal distances in equal time intervals. As you can see, a graph plotted based on the data provided again shows a curve. Now, let's look at how we can use the distance time graph to make deductions about speed. To determine the speed of an object, consider a segment PQ. of the distance time graph of an object in uniform motion. Draw a line parallel to the y-axis from point Q and another line parallel to the x-axis from point B. These parallel lines intersect each other at point R to form a triangle PQR. On the graph, PR denotes the time interval, while QR corresponds to the distance. You can see from the graph that as the object moves in time interval t2 minus t1, the distance it covers is s2 minus s1. By definition, speed is the ratio of distance covered to the time taken in covering that distance. Therefore, the speed of an object v is equal to s2 minus s1 divided by t2 minus t1. Note, you can also use the term uniform velocity in place of uniform speed if the magnitude of displacement equals the distance travelled by the object along the y-axis. Like the distance time graph, the variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In a velocity time graph, time is taken on the x-axis while velocity is taken along the y-axis. Using a velocity time graph, you can determine the nature of the motion, the velocity of the body at any instant, displacement of the body as the area under the graph, the instantaneous acceleration, and the equations of motion along a straight line. Let's consider the different cases that can be represented by a velocity time graph. Body at rest. Body with uniform velocity. Body with uniform acceleration. Body with non-uniform acceleration. And body with uniform retardation. The displacement is 0 for a body at rest, and hence the velocity is also 0. A velocity time graph plotted for a body at rest displays a straight line along the x-axis. When a body moves with uniform velocity, there is no change in the velocity with respect to time. Therefore, the velocity time graph for a body with uniform velocity will be a straight line parallel to the x-axis. The point where the line intercepts the y-axis shows the magnitude of the uniform velocity of the body. When a body exhibits uniformly accelerated motion, the velocity time graph represents a straight line passing through the origin and subtending an angle with the x-axis. This is because, in this motion, the velocity of the body increases uniformly with time. The velocity time graph for a body moving with non-uniform acceleration is a curve and not a straight line. The velocity time graph for a body moving with uniform retardation is a straight line making an obtuse angle with the x-axis. Just as you can use a distance time graph to determine the speed of an object, you can use a velocity time graph to determine the displacement of an object. The area under a velocity time graph gives you the displacement of the body in a given time. Consider the velocity time graph of a car moving with uniform velocity, say 30 meters per second. To determine the displacement of the car between points A and B, which represent the position of the car at durations 20 seconds and 30 seconds respectively, draw perpendicular lines from A and B to intersect the x-axis at point C and D respectively. The time taken, t, by the car to move from the position represented by point A to the position represented by the point B is the difference of time t2 and t1. We can say AB is equal to CD is equal to t2 minus t1 is equal to 30 minus 20 is equal to 10 seconds. Since the car is moving with a uniform velocity, the magnitude of its velocity is the same at all points on the graph. Velocity v is equal to AC is equal to BD is equal to 30 meters per second. By definition, the velocity of an object is the ratio of displacement to time. Therefore, we can say that displacement is the product of velocity and time taken. Substituting v and t in the expression S is equal to Vt, we get S is equal to AC multiplied by AB. This is nothing but the area enclosed in rectangle ABCD under the velocity time graph. Thus, in this case, the displacement of the car is equal to 30 meters per second multiplied by 10 seconds is equal to 300 meters. Similarly, you can also determine the displacement of a body moving with uniform acceleration. Consider the velocity time graph. To determine the displacement of the body between points A and E, from both points A and E, draw two lines parallel to the y-axis, intersecting the x-axis at points B and C respectively. From point A, draw a line parallel to the x-axis to intersect the line CE at D. The area under the velocity time graph between points A and E is the sum of the areas of the rectangle ABCD and the triangle ADE. Hence, the displacement is equal to S is equal to AB multiplied by BC plus half of AD multiplied by DE. Analyzing a velocity time graph enables you to derive the equations that define the relationship between velocity and acceleration of a body moving in a straight line. These equations are collectively referred to as equations of motion. There are three equations of motion. V is equal to U plus AT. S is equal to UT plus half AT square. 2AS is equal to V square minus U square. These equations are used to determine the position, velocity, and acceleration of an object. We can derive these equations graphically. The first equation of motion is known as the velocity-time relation. Consider a velocity-time graph for a uniformly accelerated moving object as shown. In the graph, u is the initial velocity of the object represented by the point A. V is the final velocity represented by the point B. T is the time in which velocity changes from u to v. From point B, draw two lines BC and BE perpendicular to the x-axis and the y-axis respectively. From point A, draw a line AD parallel to the x-axis to intersect BC at D. Now, OA represents the initial velocity u. BC represents the final velocity v. OC represents the time t. and BD represents the change in velocity in time t. OADC being a rectangle, OC is equal to AD, and hence AD also represents the time t. BC is equal to BD plus DC, which is equal to BD plus OA. Let's call this equation 1. Substituting BC is equal to V and OA is equal to U in equation 1, we get V is equal to BD plus U, or BD is equal to V minus U as equation 2. The acceleration of the object is the ratio of change in velocity to time taken. From the graph, acceleration A is equal to BD divided by AD, which is equal to BD divided by OC. Let's call this equation 3. Substituting OC is equal to T in equation 3, we get A is equal to BD divided by T, or BD is equal to AT as equation 4. Equating equations 2 and 4, we get AT is equal to V minus U. Therefore, V is equal to U plus AT. Let's now derive the second equation of motion, that is position-time relation. In the same velocity-time graph, we used to analyze position-time relation. Let S be the displacement of the object in time t. You can determine the displacement of the object as the area of the trapezium OABC under the curve. The area of OABC is the sum of the areas of rectangle OADC and triangle ABD. Area of a rectangle is product of its length and breadth, while the area of a triangle is half the product of its base and height. Area of OABC is equal to OA multiplied by AD plus half of AD multiplied by BD. Substituting OA is equal to U, AD is equal to OC is equal to T, and BD is equal to AT, which equals S is equal to U multiplied by T plus half of T multiplied by AT. Therefore, S is equal to UT plus half AT square. The third equation of motion, called position-velocity relation, is derived using the first two equations. In the velocity-time graph, the displacement of the object S is also equal to the area of trapezium OABC. Area of trapezium OABC is equal to half of OA plus BC multiplied by OC. Substituting OA is equal to U, BC is equal to V, and OC is equal to T, we get S is equal to half of U plus V multiplied by T as equation 1. Rearranging the velocity-time relation, we get T is equal to V minus U divided by A. Let's call this equation 2. Substituting equation 2 in 1, we get S is equal to V plus U multiplied by V minus U whole divided by 2A. By simplifying this expression, we get the position-velocity relation. That is, 2AS is equal to V square minus U square. Consider the movement of the seconds hand in a clock. As the clock ticks, the tip of the hand moves in a circular path. covering equal distances in equal time intervals. In each time interval, the hand subtends the same angle at the center of the clock. Such a motion, when an object moves in a circular path with uniform speed, subtending equal angles at the center of the circle in equal intervals, is called uniform circular motion. Other examples that you can relate to include the rotation of the moon and the earth, a satellite in a circular orbit around the earth, and so on. How would you calculate the velocity or the distance covered during uniform circular motion? Let's analyze the example of an athlete who is running along a circular track. The distance covered by the athlete at the end of one lap is equal to the circumference of the track. S is equal to 2 pi r. The speed of an object is the ratio of displacement to time. Hence, the speed of an object in uniform circular motion is v is equal to 2 pi r divided by t, where r is the radius of the circular track and t is the time taken to circumnavigate the track once. Thus, you can use this formula to determine the speed of an object in a uniform circular motion. This brings us to the end of this lesson on graphical representation of motion. In this lesson, you learned how to use graphs to analyze trends and derive and apply equations of motion. You also learned about uniform circular motion. The section on solved problems provides you an opportunity to review some model problems